Welcome to the third part on training of Module B of the G.EN.ESI project. Module A of this video series gives you an introduction to the two fundamental concepts of eco-design, lifecycle thinking and environmental assessment. Module B will provide you with a detailed procedure to model the product lifecycle and perform an environmental assessment. The third part of Module B will be focused on three specific lifecycle phases, providing details on how product design influences their environmental performance and how improvements can be made in order to reduce their environmental impact. This video has been developed within the framework of the G.EN.ESI project, which aims to support the integration of eco-design within the design and development process through the development of a methodology and a software platform. The methodology is presented in Module C and the platform and tools in Module D. This research project started in 2012 and involved 8 partners, 3 from academia, University of Bath, University Politecnica del Marche and Grenoble INP, 1 public institution, the ENEA, National Agency for New Technology, Energy and Sustainable Economy Development, and 4 industrial partners, Granta Design, Cyber Environment, Faber and Bunge Vectron. It is co-financed by the European Commission. The product life cycle starts with the extraction of raw materials, ore and compostables that will be used to form the product. This is the material phase. But first, what can be considered to be a sustainable material? If we compare a carbon fiber composite with pine wood, it appears that wood is better in terms of environmental impact. So, is pine wood more sustainable than a carbon fiber composite? The Boeing 787 Dreamliner is a structure made of 50% composites and is one of the most fuel-efficient airplanes today. A wooden plate would be much heavier and consume a lot of fuel. The lightness of the carbon fiber composite makes it the most environmentally sustainable alternative over wood. However, if the use is as a toilet seat, where the choice of material does not affect the performance of other life cycle parameters, the product with the less environmental impact per kilogram might be the best for the environment. To conclude, the raw material phase is crucial to define not only the performance of this specific phase, but also affect the rest of product life cycle. Like any phase in product life cycle, it is tied to the global performance of a product. When choosing one material over another, the entire life cycle consequences should be considered. The best alternative is the one with the least environmental impact over the global life cycle. Once you have defined the material to be used, the transformation of the raw ores into the final product happens during manufacturing. For many years, manufacturing has been the focus of environmental improvement in relation to product. The consumption of resources and the emissions generated during manufacture have illustrated the extent of environmental deterioration caused by human activities. Industrial sites are responsible for local soil, water and air quality degradation and for global environmental impacts such as acid rain or global warming due to the combustion of fossil fuel for energy production. This is why a lot of effort has been targeted at cleaner production. It is a continuous application of an integrated preventive and environmental strategy applied to processes, products and services to increase eco-efficiency and reduce risk to human and the environment. As with the material phase, production should not be considered in isolation, but as a constituent part of a global system that should be considered for improvement. To improve the environmental impact of the manufacturing phase, a few principles should be considered. The first one is a precautionary principle. All precautions should be taken to avoid damaging the environmental performance before the damage occurs. The second one is a preventive principle. It is better to prevent damage than trying to mitigate the effect afterwards. The third one is a public participation principle. By allowing the general public to access your process, you ease the adoption of innovative systems that support a cleaner production. The fourth one is the holistic principle. and is aligned with the life cycle system. You should not consider your production plan as an isolated element, but as part of an integrated system that should be improved at the system level. Transport processes appear within life cycle stage and between stages. The main transport considered is from the manufacturing plant to the user home. It includes transport with different means and also includes the product packaging. The transport phase is a significant environmental burden for products with a short lifespan, which requires a controlled environment such as refrigeration. This is typically the case for food, where the use phase has no impact and packaging is an important contributor to environmental impact. It is difficult for the product developer to influence logistics process, but the use of optimum packaging can increase transport efficiency. For example, when comparing the production of LED with halogen lamp, we can see the production of halogen is less damaging to the environment. But what about the big picture? When looking at the product life cycle, we can see that LED lamps has extended lifetime. This means that fewer LED lamps than halogen lamps would need to be transported to deliver the function provide artificial lighting over 40,000 hours. To fulfill this function, you will need one LED lamp to be transported but 15 halogen ones, increasing the impacts of the transportation phase by a factor of 15. Now that we have looked at the environmental issue related to the early life cycle stages of the product, in the fourth part of Module B, we will move on to two life cycle stages that are really significant for electronic product use and end of life.